Let's talk about another type of reaction, another classification of reaction. These are known as oxidation reduction reactions, or redox reactions. Just like we have precipitation reactions and acid-base reactions, we also have redox reactions. Not everything's a precipitation, not everything's an acid-base, not everything's a redox reaction. What is a redox reaction? An oxidation reduction reaction, or redox reaction, is a chemical reaction in which electrons are transferred from one reactant to another. These are important reactions, especially physiologically, in that our metabolism is based on oxidation reduction reactions. The electron transport system that you may have heard of, the electron transport chain, shows electrons being passed back and forth. So an oxidation is a loss of electrons. Reduction is a gain of electrons. You can't have one without the other. You got to have both. They're what we call coupled reactions. So if something's gaining electrons, if something's being reduced, those electrons had to come from somewhere. And they're coming from the oxidation, where electrons were being given up or being lost. So if you need a memory device to remember which one is which, there are two of them. The first one, the one I originally learned, is that Leo the lion goes grrr. Leo, loss of electrons is oxidation. Grrr, gain of electrons is reduction. So Leo the lion goes grrr. The other mnemonic is a lot simpler and a lot less fun. It's oil rig. OIL. Oxidation is loss. RIG. Reduction is gain of electrons. So Leo the lion goes grrr, or oil rig. Your choice. Or you can come up with your own memory device. So let's look at a reaction. Let's look at zinc solid plus copper 2 plus aqueous react to making copper 2 plus aqueous plus copper solid. This is going to wind up being an oxidation reduction reaction. And let's figure out how that is. So let's look at the zinc first. It's going from zinc solid, no charge, to zinc aqueous, plus 2 charge. So there's a change of charge there. It's becoming more positive. How does an atom become more positive? Can't gain protons because that changes its identity. How does it do it? It loses electrons. So oxidation, the loss of electrons. That zinc is lost 2 electrons going from solid to zinc 2 plus. That means there has to be a reduction taking place. And that means the copper 2 plus has to be being reduced. And so that we can write this as 2 half reactions. In the first one, the zinc solid is going to zinc 2 plus 2 electrons, showing how the electrons are being lost. The copper is being reduced, we said, is gaining 2 electrons. So if we write that as a half reaction, just showing what's being reduced, Copper 2 plus aqueous plus 2 electrons makes copper solid. So those are 2 half reactions. So you need to learn how to write half reactions. And when we're going to add these two together, and in the final reaction, you can't show any electrons. They've got to cancel out. Here, fortuitously, there are 2 electrons in both the oxidation and the reduction. They cancel out easily. Later on, we'll see something that's a little bit more complicated. Think of the reaction arrow as an equal sign, and that we're algebraically adding these 2 equations together. And so something's on both sides of the equal mark, or both sides of the reaction arrow, they cancel out. So we got 2 electrons in the zinc reaction there on the product side, 2 electrons in the copper half reaction that's on the reactant side. So they're going to cancel out. And so we add everything together, and the overall redox reaction is what we saw at the top, except I've in the reverse the order of them. Copper 2 plus aqueous plus zinc solid makes zinc 2 plus aqueous plus copper solid. Now comes the confusing part for many students. Oxidizing agents and reducing agents. The oxidizing agent causes the other entity to be oxidized. It is the thing that's actually undergoing reduction. So copper 2 plus ion is the oxidizing agent, because it's making the zinc solid become oxidized. The reducing agent is zinc, or zinc solid, in that it's causing the copper to be reduced. So oxidizing agent is itself reduced. The reducing agent is itself oxidized. The reducing agent causes something else to be reduced. The oxidizing agent causes something else to be oxidized. A little bit confusing, but think about it and make sure you got that straight. Let's talk about oxidation numbers. And this is a way that we can help track what's taking place, what's being oxidized or what's being reduced. And they may or may not have any real physical significance. If we're talking about ions and metals, like we just saw, the oxidation number and the charge are going to become equal. But if we're talking about covalent compounds, molecular species, where there aren't charges, these are usually sort of pseudo charges. And what we're using oxidation numbers, we may hear them talk about as being oxidation states, is what we're using them for bookkeeping purposes. So some rules about oxidation numbers. The first one is that the oxidation number of any element in its elemental form is 0. So for copper solid, zinc solid, molecular oxygen, molecular fluorine, molecular bromine, the oxidation number on each atom in all of these is 0. Remember that. Another rule. The oxidation numbers in any chemical species must add up to the overall charge of that chemical species. So in a compound, a neutral molecule, the sum of the oxidation numbers has to add up to 0, since it's neutral. If you're looking at a polyatomic ion, the sum of the oxidation numbers has to equal the charge on the ion. And we'll get some practice on this in class. For any monatomic ion, we just have one atom, the oxidation number equals the charge on the ion. So if you look at the sodium ion, it's got a +1 charge, the oxidation number is +1. Calcium 2+, the oxidation number is +2. The sulfide ion, which is 2-, the oxidation number is -2. When we're looking at nonmetals in a compound other than the elemental state, there'd also be some rules. So fluorine in a compound is always going to have an oxidation number of -1. Not talking about F2, molecular fluorine, but fluorine in a compound is going to have an oxidation number of -1. The group 1A and 2A metals we just talked about, they'll wind up always being +1 or +2 respectively. Hydrogen can either be +1 or -1. With another non-metal, it's always going to be +1. However, if it's with a metal, it's going to be -1. And so lithium hydride or calcium hydride, lithium would have a +1 oxidation number. That hydrogen is going to have a -1 in that compound. Calcium hydride, CaH2, calcium is +2, so here each hydrogen has to be -1. Oxygen is almost always -2. There are a couple of exceptions in peroxides and superoxides. H2O2, the oxidation number on oxygen is going to be -1. In KO2, potassium superoxide, the oxidation number on oxygen is going to be -0.5. We'll do these in class. You may must pause and think about this, but that's what it's going to be. Oxygen is almost always -2, except in those types of exceptions. Group 7A, other than fluorine, it's going to be -1, except when it's with some other halogen. And then it may have some other oxidation numbers, and we'll see those later on. Fluorine is always -1. The other halogens typically -1, but sometimes there are some exceptions, and we'll see those momentarily. So you need to learn, which means memorize, these oxidation numbers. So here's a periodic table showing the the S, P, and D blocks, and you can see some oxidation numbers. And so for metals, it's pretty easy. So the nonmetals that become a little bit different, a little bit more difficult, and they can either be positive or negative. When we talk about nonmetals, once upon a time, we said that they get a negative charge in a compound. That's in an ionic compound. If we're talking about molecular compounds, covalent compounds, they don't have a charge. But what's been oxidized and what's been reduced, we give them these fictitious charges, these oxidation numbers for bookkeeping purposes. And so they're the metals, nonmetals can have a positive or a negative charge. And so you look at oxygen, for example, as an oxidation number, it can be +2 or -2 or -1 or -0.5. Don't let that blow your mind. We'll get some practice with this. So let's balance a simple redox reaction. A little bit more complicated than that first one that we did. In all chemical reactions, the number of each type of atom has to balance. That's nothing new what we've been doing. But now something new in terms of balancing equations. The charge on each side, the sum of the charges on either side has to balance. So if we look at this reaction, chromium solid plus nickel 2 plus reacts to make chromium 3 plus nickel solid. One chromium on both sides, a nickel on the reactants and product sides. Up to now, we said that's okay, but the charges don't balance. +2 on the reactant side, +3 on the product side. So we've got to do some further work here because we got to get those charges to balance. So let's write the half reactions. The oxidation half reaction. Chromium solid, oxidation number 0, element in its elemental state, going to chromium 3 plus 3 electrons. We've got to get the half reaction to balance. And so the only way we can balance charges is by adding electrons for these simple redox reactions. So chromium solid reacts to make chromium 3 plus, aqueous plus 3 electrons. The reduction half reaction is nickel 2 plus going to nickel solid. To get this to be electrically neutral, you've got to, not electrically neutral, it turns out to be electrically neutral, but a better way of saying it is to be electrically balanced or charge balanced on both sides. So we have to add 2 electrons to the reactant side. So far, so good. So the atoms are going to balance, but our charges still aren't going to balance. Before adding the half reactions, remember we're going to add them up algebraically, the electrons have to balance. We've got 3 electrons in the oxidation half reaction on the product side, 2 electrons on the reduction half reaction on the reactant side. We've got to balance them. And so, like when we balance chemical formulas or we balance chemical equations, you saw a lot of times if you had 2 of something and 3 of another, we could multiply the thing that's 3 by 2 and the thing that's 2 by 3 to wind up 2 times 3 is 6. So we're going to use that trick once again. So there's our starting equation. There's our oxidation half reaction that I just carried over from the other slide. There's our, what we said we're going to multiply that one by 2. So now we got 2 chromium solid plus 2 chromium 3 plus 2 times 3 are 6 electrons. Now our reduction half reaction from the other slide, nickel 2 plus 2 electrons makes nickel solid. We said that we will multiply this one by 3. So now we've got 3 nickel 2 plus 6 electrons gives us 3 nickel solid. And so we can cancel out those 6 electrons from both of those. As we add them together, we wind up with a final molecular equation, the balanced redox equation. 3 nickel 2 plus 2 chromium solid react to make 3 nickel solid plus 2 chromium 3 plus. We've got 3 nickel on the left, 3 nickel on the right, 2 chromium on the left, 2 chromium on the right. So all of our atoms balance, like always before, but the charge is also balanced. 3 times plus 2 on the left, on the reactant side, is plus 6. 2 times plus 3 is plus 6 on the product side. So we're charge balanced. And that's our balanced redox equation. This has been a speedy run through redox reactions and oxidation reduction in general and oxidation numbers. We'll do some practicing later on. Thanks for listening.